All right, welcome back to our hyperbola lesson. This is the final objective, objective 3. I know it's not on here yet because I didn't want to spoil the picture. So the picture is interior, the ceiling of some church in Spain, Barcelona, and the shape on the interior of it makes not necessarily a hyperbola, but a hyperboloid. As we've seen in some of those other pictures, it's a three-dimensional hyperbola. Man, that's pretty impressive right there. That's a spectacular church. Anyway, so objective 3, what we're doing here is we're going to be graphing hyperbolas in standard form. So follow this with me and give you some step-by-step instructions on how to solve or how to graph these things. It should be pretty easy if you follow my 9-step program. I mean, maybe it's 5-step. Let's see. Okay, so step number 1, you're going to plot the center, the vertices, and the foci. So you're going to get the center from your HK, right? Your vertices you're going to get from your A value. And remember, the A value is underneath the positive one. It's not necessarily the bigger one. And then the foci, you're going to have to use the Pythagorean theorem in order to get it. So there's your center point. I plot that thing. I'll plot my two vertices. And if I were to draw that line that connects them, that is the transverse axis. And here, for hyperbolas, the foci are always on the outside of the vertices. And it's the exact opposite for an ellipse. The foci were always on the inside. And remember, this is just an inside-out ellipse anyway. Okay, so I've got those. What other things do I need? Well, let's go ahead and make that rectangle whose length and width are 2a and 2b. The 2b is the conjugate axis, so once you throw that thing in there, and now just construct yourself a little rectangle using the lengths 2a and 2b, like so. All right, and remember that rectangle is just there to help you graph the asymptotes. So you go from opposite corner, and throw in your asymptotes. That's what step 3 is. Draw your asymptotes to the opposite vertices, like that. Okay, and just like we've done with rational graphs before, we just have to follow those asymptotes and then make sure that our vertices touch V1 and V2. So sketch the smooth curves, the two branches of your parabola thusly. See? Oh, okay, so it was a 4-step program. So graphing hyperbolas, a breeze if you just follow my 4-step program. So let's give this a try on a couple of problems here. So number 1 and number 2. We're going to do number 1 together, and then I'm going to have you do number 2 on your own. So number 1 is the same equation that we were looking at before as a hyperbola. We had already put it into standard form. Okay, so on this first graph, we've already looked at this equation. Let's that was in general form. Let's look at the standard form. It goes like this. Wah, wah, wah. Just like that. All right. Now we need some key points here, because first step is to plot the center point, vertices. So let's go ahead and do that. So my center point is at, it's just 2, -3, right? Okay, that's pretty easy. Well, let's go ahead and get a point on the graph there, 2, -3. There's a dot there. Nice. Okay. Now what else do I need? I mean, my A value and my B value. My A value, isn't that coming from the bigger number, right? It's coming from the 9? No, it is not. A value does not necessarily come from the bigger number. Not for a hyperbola. The A value comes from the positive number, so that's this 1 here. So A value is equal to 1. And this is horizontal, so I'm going to go plus or minus 1 towards the right and the left there. So there's one vertex and there's the other vertex. Okay, my B value is coming from the other one, the one with the -1, so that's 9 squared and 9 is 3. So that's along my conjugate axis going upwards, +3 and -3, so right there. Okay, and let's see, well, what else we got to do? We got to make ourselves a little box to go around this thing, right? Maybe I should have made that in a different color. Well, I'll switch up the colors whenever I put in my asymptotes. So when I put in my asymptotes, let's go with red here. So red. I can see here that the slope of this is supposed to be up 3 over 1, so basically 3, so up
3 over 1, up 3 over 1, right? Or maybe it's down 3 and left 1. Maybe that's what it is. Alright, so there's one asymptote. Let's put in the other one. That line looks totally straight, so up 3, left 1, up 3, left 1. Keep putting them. Maybe go downwards. And one more. And dash these things in there. That looks rather handsome. All those different colors. And let's switch colors again, why don't we?
So what direction is this thing going to open up in? It is, no, not blue. How about green? Let's go with green. The squared term, the positive square term is the x, so this is horizontal. And that's where I put my vertices, right? Right? Okay, so follow the shape of these asymptotes. You know, we've done rational graphs before, and these have asymptotes on there too. That's pretty spectacular. All right, let's try this next side over here. Make it match, and oh man, it got a little shaky right here. A little shaky. I had palsy. Apologize for anybody out there who has palsy. Okay. What else did I didn't do foci. You want to do foci? Okay, we'll do the foci. Right. So let's do the foci. I got to use the regular Pythagorean theorem on this. So that's c is equal to the square root of a squared is 1 plus 9, right? B squared. Square root of 10. So I'm going left and right, the square root of 10. Square root of 10 is in between, let's see, 3 would be 9. Oh, that's pretty far out here. So it's like from the center point, 1, 2, 3, and a little piece, and 1, 2, 3, and a little piece. Well, those are pretty far out, right? The further out that I get, the more flat those things look, and okay, so that's to be expected. Okay, so that concludes this one. Now, then, let me flash back here. So you're doing number 2. Of course, the first thing you're going to have to do is put that thing into standard form, so you can identify all your key points, and then put it down on the graph. Use my easy 4-step program. Look at the time here. Okay, yeah, I've got enough time. I need to go home and check on Rowan. We had Rowan stay home from school today so that he could do a few chores. So I got to make sure that he's on top of it, not just at home, you know, watching TV or playing video games. So I'll do that. I'll come back and then we'll check our answers together. All right? All right, Rowan, pretty good kid. I admit I surprised him, right? But he was doing what he was supposed to be doing, mowing that grass. All right, great. So let's see what you got on this graph here. So whenever I look at that, I can tell it's a hyperbola because you got an x squared and a y squared. I can look at it and say it's definitely hyperbola because it's got the minus in there. Now, just because the y is negative doesn't mean that the y is going to stay negative. And that's what happens right here whenever you go to do the algebra on it. So you have to only complete the square on the x's because there was only a y squared term. It didn't have a y term in it. And when you do that, you end up with a negative 12 on the right-hand side. When you divide by both sides by the negative 12, then it switches the signs of the x squared and the y squared terms. So that's where, that's why it's sometimes difficult to just look at it and go, oh, I think it's going to be horizontal, but it's not. This one was vertical. Okay. So there's the equation there again, and then from that I can get my center point. Make sure that you pay attention to where the x's are going right here. So x coordinate is at -1 and the y coordinate at 0, so you plot that point first. And also you plot you find your a value, so you can find your vertices. So the a value is the bigger number, so the square root of 4 is 2. So I'm going up 2 and down 2 since this one's vertical from that point. And then my b value for left and right for the conjugate axis is the square root of 3. That's underneath the x there, which is about 1.7, so you just have to eyeball that. And then throw in your asymptotes from corner to corner and sketch yourself a nice, smooth, perfect, nice graph right there. It says it all nice. I think what I neglected to do on the previous one is find the foci, so I went ahead and found it on this one. C value using the Pythagorean theorem, and you get square root of 7, so I approximated that. Is it a little bit? It's right there in blue in the picture. That's nice. Okay, so you probably thought we were done, but we're not quite. Just got a couple more things to look at. That is putting this all together now. We're looking at all the conic sections together. Here I have a whole bunch of quadratic equations. Which one is what? What are they? So look at the first one. I have only an x squared term. If I only have an x squared term and I don't have a y squared term, there's only one that was like that, and that's the parabola. And I know that because this means that I have 2 zeros on the x-axis, but that's it. So I've got a parabola. Okay, the next one. I have a x squared term and I have a y squared term. Definitely not a parabola. But my x squared term and my y squared term are separated by a minus sign, which makes this one a hyperbola. So that minus sign means inside out ellipse. There we go. All right, on number 3, again we have an x squared and a y squared. However, the coefficients are different. So if the coefficients are different, this is not going to be a circle, it's going to be an ellipse. And you can also tell a little bit more about it. Since the x squared has the smaller coefficient, it's going to end up with the larger number in the denominator, which means that the major axis is going to be horizontal on this one. So let's make that note. If I go back up to number 2, can I tell that the transverse axis is going to be horizontal because this one's positive? No, not yet. You'd have to actually put it in standard form in order to see that for sure. Okay, finally number 4, just by a process of elimination, we know which one this one is, right? But if I just look at this, I've got an x squared and a y squared. It's like we've had on the last 3, separated with a plus sign, and the coefficients this time are the same. So the x's and the y's are scaled by the same number. This makes it a circle. So that was not bad at all, right? Putting those things all together. Okay, and then here's one last application, and there's no work to do. It's just a very interesting way to link all of these conic sections together. So we've seen this picture before, and we've talked about how the orbits of things, like the orbit of our planet around the sun, is an ellipse. Okay, and for a really, really long time, people didn't think it was an ellipse, thought it was a circle because it wasn't a very stretched out ellipse. But now we know that it is definitely an ellipse. But sometimes orbits of things could be a parabola or a hyperbola as well. It all depends on the velocity. So here's some formulas from physics here. So in these formulas, v is the velocity of whatever object we're talking about. Could be a comet, could be an asteroid, something like that. And then inside the square roots there, you got g, which is the universal gravitational constant, and you have m. M is the mass of the object, however heavy that thing is. And then P, if you look in the picture, P is just the distance from the sun. The sun is sitting at one of the focal points, one of the foci of our ellipse, and then to the actual object, whatever that is, whenever it enters into our elliptical orbit. So if the velocity is smaller than that quantity, you get yourself an ellipse. So basically it gets trapped in by the sun's gravity and it just keeps going around the sun. That's us, right? Okay. If the velocity is exactly equal to that quantity, then it can escape. It can escape the gravity and it can keep on going, and the path that it's tracing out is a parabola. And then finally, if the velocity is a little bit more than that quantity, then not only does it escape, but its trajectory is a hyperbola. And of course, both in case number 2 and 3, the hyperbola and the parabola, we'd never see those things again because, well, that's the shape of the graph, right? So that's a very interesting application, nice way to tie all of those conic sections together. Okay, so this is it. Our lesson on hyperbolas, where we're talking about the definition of a hyperbola versus a conic section. Like you can see it there in the picture. You're cutting the plane, or using the plane to cut the double nap cone perpendicular to the basis, and as a locus, where you're measuring a point's distance away from the two foci and you're subtracting that, staying constant, and that's 2a, remember? That's the length of the transverse axis. We also wrote the equations of our hyperbolas in standard form, and we graphed them in standard form. So here's your assignments. There's Rowan saying hi, hyperbola. And one last thing that I'm going to ask you to do. One last thing for class tomorrow, and that is I'd like for you to bring a flashlight to class. You think you can do that? You think you can bring some sort of flashlight to class? That'd be really cool. All right, see you guys in class.